Welcome back. We are ready to look at two different kind of specs for the second order system. We are going to look at the natural frequency. So what do we mean by the natural frequency? Natural frequency is when the damping ratio is equal to 0. So that means the system is oscillating, and we call that natural frequency as omega n. So when the system oscillates, we call that the natural frequency. Let me write this as oscillate. Now let's talk about the damping ratio. This is all going to help you to solve problem number 2 as well as problem number 3 on homework number 2. So the damping ratio we indicated by zeta is actually the ratio of the exponential decaying frequency to the natural frequency. Okay, so exponential decaying frequency to the natural frequency. So this will come a little bit more if we take an example of the damping ratio. However, we have to first look at a second order system and represent it in this format. GFS is equal to omega n squared s squared plus 2 zeta omega n s plus the omega n squared. Well, in order to find the poles of the system, the transfer function must go to infinity. That means the denominator must be set equal to 0, and here we can apply the quadratic formula to find the roots of this equation. So obviously it is going to give you two poles. It's a second order system after all. So b here, is minus 2, applying the quadratic formula, if you recall, minus b plus minus b squared minus 4ac, right? So that would be 4 zeta squared omega n squared minus 4ac. Okay, well, a is 1 and c is that, so that would be 4 omega n squared, and the whole thing is divided by 2. Well, if you apply a little bit of math, you can factor this out, and what you are going to get is this: minus 2 zeta omega n plus minus 2 omega n will come out, and inside you're going to have zeta squared minus 1. The whole thing is divided by 2. Well, as you can see, there are two roots, and this will cancel out. So shall I write these two roots right here for you? And that will be equal to minus zeta omega n plus minus omega n, which is the natural frequency, zeta squared minus 1. And this is pretty much, you're going to see in all the textbooks, that it has got two poles. It's a second order system, so 1 and 2 poles, right? Now, if you look at this equation right here, if zeta, the damping ratio, this is where the damping ratio, this guy is the damping ratio, concept will kick in. If the damping ratio is 0, then you will see this will go away, right? This will become more or less like an imaginary, right? Because the zeta squared is 0. 0 minus 1, square root of minus 1 is going to give you imaginary. So you'll have two imaginary poles here. And you recall from the previous discussion, that becomes an undamped system. It means it's oscillating. So whenever zeta is equal to 0, which is the damping ratio, we have a natural frequency, and the system is oscillating now. If zeta similarly is between 0 and 1, you can come back here. You will see from this equation that you're going to have two complex poles. So this, recall from the previous discussion, this is called the underdamped. And when zeta is exactly equal to 1, guess what happens? Zeta is equal to 1, this will go away. Then you will have two real poles at the same location minus zeta omega n. And this is this guy right here. So this becomes critically damped. And similarly, when you come here, when zeta is greater than 1, then you are going to have two real poles, which is overdamped. So I will see you shortly in the next video. Thank you.